Okay, getting started with flight controls. Flight controls are covered in ATA Chapter 27. So when you're looking at manuals or IPCs or other things like that, that's going to be where you find that. Not only is it flight controls, but we just finished up hydraulics. Something like the flight control actuator, right? It's a hydraulic actuator, but it's tied to the flight control. Often those may be found in Chapter 27. It depends on the manufacturer and where exactly they decide to split their system. So, if you're looking for a flight control actuator, you may have to look in 27 with flight controls, or you may have to go into hydraulics in order to find it. So flight controls, you've learned some of these. You've talked about probably the three main ones and some of the others, whatever, in your basic systems class, right? And they're grouped into roughly two major groups, primary and secondary flight controls, with the primary flight controls being made up of ailerons, elevator, and rudder, and the secondary flight controls including flaps and trim that you've probably seen before. But on larger aircraft, we add slats and then spoilers and speed brakes as well to that list. For any flight controls to really understand what's going on, they're designed with a kind of underlying theory of operation called a loop of control. And I put this in flight controls, but understand that this is used in almost everything we do on a transport category aircraft. This situation where we provide some kind of an input, a control takes place. In the case of flight controls, it's your servo valve and actuator. And then we're going to have some kind of feedback or follow-up from, in this case, the flight control to stop cutout operation, basically stop the flight control where we've told it we want to go, and also provide verification of movement or change. But this same loop of control is used in many other systems as well. Anyone have an example of where else we've seen this so far? And I've mentioned it a few times in some other labs, just not as directly. Any ideas? No? What happens when you turn on a hydraulic pump in the 727? What happens directly above that switch? A light shuts off. There's a low pressure light. Okay? That light is not shut off by moving the switch. Okay? In that case, your input is you've moved a switch. The control is it sends electrical power to the hydraulic pump. The hydraulic pump begins to operate, and just after the hydraulic pump, downstream of it, there's a pressure switch. And when pressure is sensed, it sends feedback up and shuts that light off in the cockpit. So you know that the hydraulic pump is turned on and is making pressure. Okay? Same thing happens though with flight controls. You put an input and somehow you get feedback. Now on a basic small aircraft, that feedback is when you move the flight control, you get air pressure against the flight control, you can feel it. Okay? Larger aircraft, we have to include it into the operation. We'll show why. So we can position flight controls where we are requesting them to be positioned by moving the inputs, control column, rudder pedals, whatever. But then we also want to make sure they're actually operating like they show. Many ICAS aircraft for flight controls have indication of flight control position on one of your ICAS screens. And the way that works is you do an input by moving the input, whatever it is, yoke, pedals, flap handle in the cockpit. It causes a control action to take place on the flight control. And then the flight control moves, it has some kind of a position sensor on it. And that sends a signal back to the ICAS display that shows that position on the display. Okay. So this has to take place though in our flight controls themselves. So I've got a video that kind of shows this happening with hydraulic flight controls. I'm going to play that for you real quick. We're going to work our way through this video as we go through the lecture. So I have here 6 different flight control configurations. So actuation and control. Some people would actually break this last one into 2, making 7. And then there's some different variations on each one, but basically speaking, when we're looking at flight controls, flight control actuation is the force or what physically moves the control, okay? And then the control is how does that signal get from the flight deck, from the operator to the flight control itself or to the actuator, okay? So actuation is the physical movement of it. Control is how that signal is transferred. So the first one is mechanical actuation and mechanical control. We'll talk about that. The second one is mechanical actuation with what's called hydraulic boost. So it's still a mechanical control, but it has hydraulic boost. This is how the power steering in your car works. That's what you would probably be most familiar with, is where if your power steering stops working, you can still steer, but it's very hard, right? You don't have anything helping you. It's electric, yeah, in cars nowadays. Hydraulic then, the third one is hydraulic control. Sorry, hydraulic actuation with mechanical control. Okay, so we take a hydraulic actuator to move the flight control. Mechanical control, that's things like cables, push-pull rods, all that kind of thing connecting you. Okay. That's what we see on the 727. Hydraulic with electrical control, so a hydraulic actuator with an electrical control system. We don't have any examples of that here, but that's known as, we'll look at it, it's called fly-by-wire. Electrical control and actuation, so an electrical signal that's driving some kind of an electric motor or linear actuator. And then finally, we have what's called light control. And the reason we can break it into two is because light can be used to control either electrical and or hydraulically actuated components. And that is, you use fiber optic signal cables for that kind of equipment. So your purely mechanical flight controls, as I mentioned, when I'm talking mechanical, these are your cables, bell cranks, push-pull rods, torque tubes, and those kind of things that you've seen in smaller aircraft, right? Every aircraft we have in the hangars down there for you to work on uses this kind of a flight control system, right? The 182, the 172, the Baron, and the King Air use some kind of combination of cables, bell cranks, push-pull rods, torque tubes. The Mooney uses push-pull rods and torque tubes. It doesn't use any cables. But they're both considered a mechanical flight control system. But your power here is limited, right? It's the strength of the pilot or operator pushing on the yoke, pushing on the column, moving the rudder pedals, that's going to operate things. And usually where these kind of max out is in the medium-sized turboprop area, 34 passengers or below, actually about 32 passengers or below. The next step are these hydraulically boosted mechanical flight controls. So here you still have a mechanical connection to your flight controls, but for certain flight controls, it may be tiring. It's typically too tiring for a crew to operate them, purely mechanical. So we add a boost to help them out. And again, like I said a minute ago, this is like the power steering in your car. So you still have a direct connection. What that means is if your hydraulics fail or your electrical fails, you still have the ability to move those controls. So on aircraft that have these, they may have a hydraulic, the hydraulics that drive them may not be as redundant as a larger aircraft, because you can still have a reversionary mode where you're mechanically moving the controls. So the 34 passenger turboprops I worked on had the ailerons and elevator were purely mechanically controlled. The rudder was this hydraulic boost setup. Okay? And it only needed one hydraulic system because you still could move the rudder even if the system wasn't running. So the video that I'm going to switch back to shows how this operates. Okay. So you can see in the video how with this kind of a system that flight control can operate both in a manual mode and that boosted mode. But you'll have limited control authority when it's purely operating as a mechanical control. But that's also why aircraft that have these may not need the 2 or 3 hydraulic systems as backup, because they still have the ability to move it. The next type of flight control we have are mechanically controlled, hydraulically actuated or operated flight controls. And this is what we, like I mentioned earlier, what we see on the 727. This is probably what's on most common up until the latest, some of the latest generations of aircraft, okay, in some form or another. So here we eliminate the physical connection between the input, the yoke or the side stick or whatever, and the flight control surface itself. So now we can no longer move the flight controls if we don't have a hydraulic system operating. And that's where the requirement, where if we go to an aircraft that's large enough that it needs fully mechanic or fully hydraulic flight controls, we also need to have enough redundancy built into the hydraulic systems that the chances of losing them are minuscule. And so that's where you start to get into aircraft that have to have a minimum of 3 hydraulic systems. And each of those hydraulic systems has to have a minimum of 2 power sources. You know, often an engine-driven pump and an electric pump, or 2 electric pumps that can get power from either engine. You get electricity from either generator. So if we have a total hydraulic system failure, you do have the potential to lose flight controls. And this did happen before. There was a plane that kind of crashed. It crashed in Sioux City, Iowa. It was a DC-10, took off out of, I believe it was Chicago. And they had, on the DC-10, it's a 3-engine aircraft, 2 engines on the wing, 1 in the tail. And the engine mounted in the tail had an uncontained fan failure. So the fan of the engine came apart. And when it came apart, it hit hydraulic lines that went up into the tail for 2 of the 3 hydraulic systems. And then it also, that was the only engine that drove the 3rd hydraulic system. So it lost all hydraulics. And in that case, the crew was able to barely fly the plane by using differential thrust of the 2 remaining engines. So if you throttle both engines up, the nose pitches up. If you throttle both back, the nose pitches down. If you throttle them one at a time, the plane's going to yaw left or right. And they almost landed it at Sioux City. It rolled over at the last minute, but they saved. Several of the crew members survived, and about half the passengers survived. So, and they've done simulators after that, and no one's really been able to fly it for the length of time and distance that they were able to. So it's pretty amazing. But yeah, well, and there was a 3rd off-duty pilot who came up and sat in the jump seat, was working the throttles. So he actually did a talk. He would come to Western every now and then and do a talk. I don't know if he'll come back anytime soon, but with a total hydraulic system failure, that's what you end up with. So we have to have that redundancy. So for these, when we have with these fully hydraulic flight controls, we have 2 types of valves that we're going to use with them. So the first is a valve in a power control unit. And that's the servo valve and feedback link. And that's similar to what's in the video. So we'll go back to the video in a second and look at those. Before I go to those, I want to talk about the second type of control valve, and that's a full travel actuator. And that's your typical hydraulic actuator without the servo feedback on it. So it basically is when you put the valve in position A, the actuator, say, fully extends. And when you put the valve in position B, the actuator fully retracts, and it's not going to stop at any specific point based on what kind of an input. It's basically going to be all the way open or all the way closed or all the way extended or all the way down. This is like what a landing gear, right? It's rare we would stop a landing gear anywhere between fully down and fully up. So that these full travel actuators use something like that. In flight controls, the one spot where we sometimes see full travel actuators is if an aircraft has what are called dedicated ground spoilers. And spoilers are panels that come up on the top of the wing. We'll talk about them a little bit later. But a ground spoiler typically is flat with the top of the wing, flush with the top of the wing in flight. But then when the wheels touch down, they pop up like this to disrupt the airflow over the wings to spoil lift. And so if you have dedicated ground spoilers where the only thing they do is pop up when the airplane lands, they may have these full travel actuators. But otherwise, almost all your other flight controls are going to have some kind of a proportional power control unit in order to be able to adjust not just the direction they move, but the magnitude of deflection that they have. So let's watch the rest of that. The video kind of finishes up with this style of flight control and actuation. If we look at how one of these is installed in the aircraft, the videos have a real short linkage, but here's a little bit more typical kind of setup. So we have our yokes up here. You can see each yoke, so these are for the ailerons, have a run of cables, just like we looked at doing the flight control lab. There was a pair of aileron cables for the pilot yoke, a pair of aileron cables for the co-pilot side. They're interconnected normally, but they have the ability to disconnect in case one of these cable runs gets jammed up. Those go to various pulleys and torque tubes and bell cranks that move cables that go out. And here are that's what I was talking about, the PCUs instead of PFCUs. And here it shows there are 2 PCUs in the left aileron and 2 PCUs for the right aileron. And what happens is either run of cables can operate the ailerons independently. And then if they get jammed up, you can disconnect them at the yokes, and then either just the pilot or just the first officer can fly. And then the other part of it is that bypass valve that opens would deactivate a PCU if there was a hydraulic failure, so that the other one is able to move the flight control. Now, if that's the case, the one thing you do have is, one PCU is half as strong as 2. And so if you're only operating the flight control with a single hydraulic system and a single actuator, it may result in some slightly reduced control authority. Okay, the plane may not be able to roll as fast, you may not be able to deflect the flight control as quickly, but you can still maintain enough control that the aircraft is flyable. So, other things you'll see, we'll talk about them a little bit later. There's a feel unit and trim actuator that can feed into this, which allows us to control trim. The feel unit is, as it showed, there is no feedback. There's no, the air pressure forces on this, say, aileron are not going to feed back through the cables to the yoke. And so later on in the lesson, we'll talk about artificial feel systems in order to provide that aerodynamic feedback to the operators. The other thing that feel unit often does is it will recenter the yokes if you let go. So in the video, they showed if you move that stick, if you deflected the stick and then let go, the flight control would stay in that position. On an aircraft, we typically want it, if you let go, we want things to return back to neutral. And so that feel unit will also, that provides a spring, that's trying to put the yoke back into the neutral position. This is an Embraer example, so it's got Embraer style ram's horn yokes where you hold them like this. So Embraer's like this, Boeing's like this, Airbus is like this. If you're not familiar with yokes and sticks and whatnot. But it's going to put that yoke back into the neutral position if you let go of it, which also will then put the flight controls back into the neutral position. The next type of flight control we have is an electrically controlled. So now our signal to move the flight control, instead of being sent via cables and push-pull rods and bell cranks and tubes, now we're going to do it electronically. We're going to do it over wires. So hence the term fly-by-wire for an electrically controlled. And here we have a hydraulic flight control system. It still uses a device called a PCU or PFCU to move the flight control, the actuator. Okay. But the input to the actuator, instead of mechanical linkages moving a valve physically, it's going to be that electrical signal, which moves like solenoid valves and what are called torque motor valves, and those are able to move it. So again, though, we cannot move the hydraulic, or can't move the flight controls if we have a hydraulic system failure. We also now have a case where an electrical system failure could prevent us from moving flight controls. And so again, we've seen the redundancy built in to our electrical systems. That plays a part in allowing this to be the case. The computers, there's a computer that's going to translate the movements of the inputs to the signals being sent out to the flight control. They're going to be redundant computers, typically 2 or even 3 computers that can control the flight controls, or computers for certain flight controls, you know, two flight controls, or 2 aileron flight control computers, 2 elevator, you know, things like that. Some of them are combined, some of them are separate. You can see we had a SFECU, FECU, slat flap electronic control unit on our airplanes. Another airplane had a FECU flap electronic control unit. We had our steering, our nose wheel steering was fly-by-wire. Steering control, okay. So an airplane doesn't necessarily have one type or another. The airplanes I worked on, some of them had some combination of fly-by-wire and mechanically operated, hydraulically actuated flight controls. But our PCU servo valve, they're going to be 2 types again. So we can have a PCU servo valve. This is the same concept we saw with the mechanical servo valves in the video, but that feedback is now going to be provided by a sensor rather than a linkage connecting back to the valve. Okay, and these are known as RVDTs or LVDTs. And we'll look at those in detail in a second, but that stands for rotary variable differential transformer and linear variable differential transformer. And then there's also full travel versions of these where they don't have that proportional control, where it's just going to move one way or the other. So again, going back to like that speed brake example, it could just open. It could have an electrohydraulic valve that would just move the speed brakes to the up position when the wheels touch the ground. So these fly-by-wire, there is no more physical connection between the stick and the yoke surface. And those 2 valve types, we're going to look at the transformers here when we get back from break. So let's go ahead and take a break, and then we'll look at how these transformers work.